Welcome back. We want to continue from where we stopped, looking at another supervised learning algorithm called decision tree. Decision tree is essentially like a model that makes predictions by splitting data into smaller groups based on input features. It repeatedly divides the dataset using the most informative features using until each group contains similar outcomes, classification, or values regression. All right. Decision tree can be used as a classification model or regression model. So it works by splitting the criteria at each step. Select the best feature to split the data by itself. Best means the feature that maximizes of information gain, which reduce uncertainty or entropy the most. And in the stopping condition, it stops when all the samples in the group belong to the same class. Further splitting or further split the that it don't improve the production. After stopping, further split does not improve prediction. In the final output, the result is a set of if-then rules used to classify or predict new data. So if this, then this. If this, then this. All right. So the key term is called information gain, which measures how well a feature separates data. And then we have entropy, which quantifies disorder, or lower entropy means more purity in groups. Now, this approach is interpretable and works well for both classification and regression tasks. So, which means that a decision tree can be used for both classification and regression. So, there are many other algorithms that can be used like the same way like that. It's also what they call it, a random forest also can, and also some machine can also be used as both. All right. So, for example, the example of a binary tree predicting whether a person is fit or a person is unfit, providing various information or features like age, eating habit, exercise habit, and so on. So it's just a simple example. So let's say somebody has supplied these features, age, eating habit, exercise habit like that. Want to use it to binarily check whether a person is fit or unfit. So this is how it looks like in the decision tree. Person age is 30 is a question. If yes, eat lots of fast food. No, exercise regularly. Eat lots of food. Yes. Unfit. No, fit. Exercise regularly. Yes. Fit. No, unfit. So you just if condition, if condition that what is used is so in the above three, the question are decision nodes and final outcome are leaves. So the final outcomes are the leaves. All these ones they are leaves. So these are the nodes. So that is how it makes prediction. So it's as simple as that. And here are the two main decision tree algorithms. We have what they call classification tree and regression tree. So the first is a tree that categorizes data into distinct classes. It creates rules by splitting data based on feature group values, ultimately assigning each group to a specific category. And regression trees predict continuous numerical values. It partitions data using feature thresholds and assign each segment in an estimated numerical output. So that's when you have your square mean error and the rest of them. So this is for regression type. So you can do the same. So for example, key differentiation output discrete categories such as spam, not spam, like the one we did last time. And regression output numbers, e.g., house price, temperature, that the one we do for linear regression the other time. Multiple ratio, that is similarly, okay, that's what it does. Both are hierarchical splitting, but differ in their prediction types. Okay, so the key assumptions for this model is that the first is root node. The training data serves as the starting point, which is the root node for building the tree. And the feature types works best with categorical features. If using continuous values, they must be discretize, that is bin into categories first. Then recursive splitting, data is repeatedly divided into subsets based on attribute values. And attribute placement, a statistical approach, e.g. information gain, Gini index, determines which feature becomes the root node and how internal nodes are structured. So why these assumptions matter? Because it ensures optimal splits for accurate predictions. It maintains interpretability in decision rules. All right, so let's look at a sample briefly of decision tree. Loading the data set now. I mean the portal libraries that we need. We're going to use Iris as a sample for this time around. Then we do to our data set, our selection models. Model selection here, we want to use test and training split. Decision tree classifier also is loaded here. Okay, under decision tree. Metrics is also loaded. We want to use function matrix and aggregation reports. So if you want more, you can also load here. All right, so this is just usual thing we have used several times. So that what should be understood by now. So we load our data set also. So it gives us this one which we have used several times. Okay, so our y-axis, which is our y, which are features, stepper length, stepper width, beta length, beta width. So our target is a 3 classes we have here. Okay, so we see sample, we print it out to see the sample how it look like. So you can see they are all in centimeters. Okay, so it's just a sample output. Now we can split data in, we can split the data now. We split the data now. We have training and testing set now. We are using 20. This time around we want to use 30 by 70. So that 30 means testing, 70 means training. So you can use 20 and see how they look like anyway. So now we print training set size as a, and as usual. So total number there we have 105 now. We have total 150 observations. So then we split it now and 4 columns. So here we have create our we train our decision tree. So we call it decision tree DTC. We train the model here. All right. Now after the model has been trained and fitting, then we create we make the prediction here. Just click on prediction here. Make prediction. Okay. We predict the data here and we evaluate our metrics. So just pass our feature here straight for testing. Test it. The testing features here to predict. So this is just a repeated concept we have done several times. All right. So don't forget, during the training session, we pass down the training here. Okay. See, we are calling the classifier here that we fit in here. All right. So it's our S train and Y train. So it was training, but during the testing, just passing our predict by testing here. All right. So we find our matrix here. All right. Just by running the accuracy, we also try to check the you can make the accuracy 2 decimal points. You know how to do that now. All right. So you just look at our function matrix here. So we're having this accuracy here, approximately 98%. So you can visualize our tree now by using 2 methods. You can use a graphics method, right? So if you run by graphic method, you have this you have to call graphics export. Most time it's not always installed. You have to install it. This particular graphics, you have to install graphics. All right. Now also this graphic, you import it. Then also you have to okay, you just call it when after using it, you have to call the library here. All right. So now we have this tree now. This is a tree now output. Can you see? So this is our output. So the other way to use it, to use a using none for automatic label. So automatic label, we use none. All right. So that it does it by itself automatically. All right. So we let Scikit-learn generate default variables for it automatically by itself. So now you can look at the output here. It give us similar stuff, but the values are not the same here because the labels are generated by the Scikit-learn. So not by we didn't pass it across like this one. This one we did here, that you pass our label here. You see, our label was passed here by ourselves. Here is the target name. So, but here we don't pass any labeling. Let it decide. But they have the same structure actually, but not actually the same values. In here, can you see the values are different, but and not the same. So that is a simple example of addition tree, okay, that we just describe now. So it's a very powerful classification algorithm, and it was later extended by random forest, which we are not going to look at because that's what we have looked at in the first part of our example during the introduction to machine learning. So that's what we used to demonstrate, even though we didn't print out the chart, but at least we were able to cover up. So thank you so much for listening. We'll continue from there in the next class. Thank you.